It's a pleasure to be speaking to everybody. I'm speaking from my house in Santa Fe right now. That's helpful to people to visualize in this rather nebulous place online. This picture on the initial slide of my talk is a picture that Craig Allen took in the Jemez Mountains after the Las Conchas fire in August 2011. If you look closely, you can see holes in the ground where trees were burnt right out of the ground, and then those horizontal lines on the ground, places where logs were laying on the ground and then they were burnt. And this picture just kind of nicely captures what must have been an exceptionally intense fire. To go on the next slide, I'm going to be speaking mainly about the findings that were published online in Nature Climate Change in September in a paper about temperature and its influence on forests, drought stress, and tree mortality. The paper focuses on the southwestern U.S., but it really focuses on the Southwest as an excuse to use a lot of really good data in a place where there have been recent intense drought conditions. But I think the implications are much larger. When I talk about the Southwest, I'm talking about this area within the red lines here, but I'm really the implications of this study go beyond those political boundaries. I just use those political boundaries on this map for convenience. This map, by the way, is of MODIS satellite-derived normalized difference vegetation index, vegetation greenness. And the question I wanted to answer in this study is, how important is temperature to forest drought stress and tree mortality in the Southwest? And the reason I want to ask that question is, of course, because like most places on Earth, temperature has been warming for the last century. Impulses and the last 20 to 30 years have been a rather large pulse of warming. And the last 20, 30 years of warming have been accompanied by declining precipitation, but it's important to recognize that the decline in precipitation over the last 20 or 30 years has really just been a correction back to the mean after exceptionally wet 1980s and early 1990s. So while the 2000s in the Southwest have been drier in the 80s and 90s, they haven't been too much drier than the long-term average. Although it's important to note that some parts of the Southwest have been drier than the long-term average. I believe the Flagstaff area, for example, has been drier than long-term average in the last decade or so. The warming is important because it intensifies the evaporative demand of the atmosphere, or the atmosphere's ability to hold moisture. This graph here is showing the relationship between maximum daily temperature during any given month since 1895 and the Southwest's vapor pressure deficit, or effectively the sponginess of the atmosphere. How much water vapor is missing from the atmosphere? And we can see that temperature is the main driver of this. While the actual amount of water vapor in the atmosphere is really important too, in the Southwest, the exponential relationship between temperature and saturation vapor pressure causes temperature to be really important. In 2011, 2012, as I'll show in a little bit, vapor pressure deficit has been higher than any other time on record, and so those highest dots represent the Junes and Julys of 2011 and 2012. And so now I'm showing a time series of regional climate where we include vapor pressure deficit. And in the past decade or so, vapor pressure deficit has on average been about 12% greater than the long-term mean. And so I adjust that hypothesis I showed a little bit ago, or the goal, rather than figure out how much temperature is important. I really want to know how much is atmospheric moisture demand important. And as I showed, temperature has a large influence on atmospheric moisture demand. And I want to answer this question using tree rings. Here's a nice picture that my friend Dan Griffin took. And wide tree rings represent years of good growth. Skinny tree rings represent years of bad growth. And in this study, we used tree ring records from 335 sites in the Southwest. We looked at the three primary conifer species in the Southwest. That's pinyon pine, ponderosa pine, and Douglas fir. Each of those species is approximately equally represented in this region. If we take all 335 of these tree ring records together and put them into a principal components analysis and just shake out the first primary principal component, then this is what we get. This is the regional tree ring record for the Southwest. Lower values represent periods of poor growth, like the 1950s and the most recent time, and the very early 1900s. And higher values represent times of good growth, like the 19-teens and the 1980s. Very interestingly, if we do the same calculation, the same principal components analysis, for each of those three species independently, they show almost identical tree ring records. And this is surprising to me because pinyon pine and Fonders pine, Douglas fir all live in fairly different places. Pinyon pine tend to grow in dry, warm places. Doug fir tend to grow in cool, wet places. But they still agree on what years should be the good years of growth and what years should be the bad years of growth. And that means that they're all dancing to the same tune. And the tune is regional climate and very likely regional drought stress. And so I wanted to find that out. What are the climate variables that drive the regional variability in forest drought stress? So we looked at two variables. We looked at seasonal precipitation and seasonal vapor pressure deficit. And again, I'm interested in finding out how important is vapor pressure deficit relative to precipitation. So we looked at 6 seasons, the 4 3-month seasons that we consider the growth year, and then two seasons prior to the growth year. And those two variables, so we really have 12 potential predictors of forest drought stress in the region. And the first predictor that comes up in a stepwise multiple regression is May through July vapor pressure deficit. And this makes sense. When vapor pressure deficit is high during May through July, which is the period, the 3 months when vapor pressure deficit is highest in the whole year, then trees close their stomata and evaporation rates are high, and they grow less. With this variable alone, we can count for about 42% of the variability in tree ring records between 1896 and 2007, which is pretty darn good, but it's obviously not near perfect. And so now if we take the residuals of this relationship, see if there's another variable that accounts for the unaccounted for variability here in a significant way, we see that variable is wintertime precipitation, November through January. A winter with higher precipitation obviously leads to more growth, and this is a very well-known relationship in the Southwest. In fact, it is, I believe, presumed to be the primary mechanism driving forest drought stress in the Southwest. Finally, we do this one more time. We're counting for 61% of the variability now, and if we add one more predictor, which I'm trying to do, if we had one more predictor, then the prior late summer and early autumn's vapor pressure deficit shows up as important. With these 3 predictors now, we're accounting for 75% of the variability. But of course, there's no strict rule that says the climate is only allowed to influence trees in 3-month chunks. So now let's see if any of these seasons should expand or contract to optimize correlation. And the only season that does is the wintertime precipitation season, where now winter precipitation is considered to be November through March. And with these 3 variables, we're accounting for 82% of the variability. And just to simplify things, we're going to turn them into 2 variables, where we take these 2 warm season vapor pressure deficit predictors and take the average of them to just have one warm season vapor pressure deficit predictor, and we see that the correlation doesn't change at all. And so now I'm interested in knowing, okay, well, which is more important, precipitation or vapor pressure deficit? And so we'll just play a really simple statistical game where we first pretend that only precipitation contributes to the predictive power of the climate tree ring relationship. And we see that with precipitation alone, we can explain about 45% of the variability in interannual tree ring variability in the Southwest. And on the other extreme, if we use vapor pressure deficit alone during those 2 warm seasons, then we can explain 58%. And if we optimize the combination of the predictive powers here, then we end up with warm season vapor pressure deficit contributing to 56% of the predictive power, and cold season precipitation contributing to the other 44%. Together, they're combining again to explain 82% of the regional tree ring variability. And that can be expressed in the forest drought stress index equation like this, where now rather than calling this the regional tree ring record, we're going to call it the forest drought stress index because it's really driven by drought-related variables. And the equation on the top is the equation we can now use to take climate data to predict the regional forest drought stress. And this is important because we don't have tree ring data into the future. This record, as I said, just goes through 2007, but now using climate data from 2008 through 2012, you can see on the right side of the graph that 5 new years of forest drought stress data have appeared. These new years of forest drought stress data have appeared because we just used climate data. That'll become important a little bit when we use model projections of future climate. So we see this really nice relationship between regional forest drought stress, at least in the trees that were sampled for this analysis, and climate data. What else does the forest drought stress index, or this FDSI, correspond to? Well, one thing it really corresponds well with is the regional summertime greenness. Remember at the beginning I showed that plot, or the map of the NDVI, the greenness of the region. Now this is an annual record of summer greenness in the Southwest, and if we throw the forest drought stress index on top of that, we see a very nice relationship. This is indicating that not only is the forest drought stress index representing the several thousand trees that were used in this study for the tree ring records, but it's representing kind of a regional interannual as well as decadal variability in the productivity of the entire forest ecosystem. Notice 2002 is the year with the lowest greenness and the lowest forest drought stress index. 2002, as I'm sure you remember, is a really important year. Sorry, I'm trying to. Okay, I thought I had a slide here, but it seems to be gone. Well, I was going to say 2002 is actually one of the most drought-stressed years in the entire Southwest, and that year led to that year and the other drought years around it, 2001 to 2004, really led to a bark beetle outbreak. This map that I hope everybody is now able to see is showing the region that was the regions that were impacted by bark beetle-induced mortality. All the orange areas that you're looking at are areas where it was estimated by the Forest Health Enterprise team that at least 10 trees per square acre or per acre were killed by beetles. And now I'm going to. Seems like I'm having some technical difficulties here. I apologize. Somehow my slides are going in reverse. But now you should be looking at some pictures. I'm going to skip through this and just say that a lot of trees in the Southwest died during 2002 to 2004 due to bark beetles. Now you should be looking at a graph of the percent of pinyon pine trees that were dead according to forest inventory and analysis data from 1997 through 2009. And you can see that among pinyon pine, which are the hardest hit by the beetle outbreaks in the Southwest, there was approximately a doubling to tripling in the proportion of dead individuals in the Southwest. And this isn't just the case for pinyon pine. It's also the case for ponderosa pine and deadwood fir, a doubling to tripling in the proportion of these species that were found to be dead in the Southwest during the mid-2000s due to bark beetles as well as wildfire, as well as just outright drought stress. One way in which beetles die is, of course, bark beetle area. So now we're coming up toward the slide that I accidentally started on a second ago. The orange time series here is annual area where at least 10 trees per acre were killed by bark beetles, or at least estimated to have done so between 1997 and 2011. And if we now superimpose the forest drought stress index on top of it, smoothed by 2 years, and now you see that the forest drought stress index axis has been reversed, we see really strong correspondence between the intensification of drought conditions in the early 2000s and the bark beetle outbreak then a subsidence of drought conditions in the late part of the decade, and a decline in bark beetle activity, and then in the last few years, again, a resurgence of bark beetles corresponding with an intensification again of drought stress. An important aspect of this figure is that the bark beetle axis, the y-axis on the left side, is exponential, or it's a log axis. And what this suggests is that even though we have a fairly short time series and there's a lot of autocorrelation here, it looks like there's an exponential relationship between forest drought stress and bark beetle impact in the Southwest. That is, a small intensification in drought stress can lead to a large increase in the vulnerability to bark beetle outbreak in the Southwest. And here again is this map that I showed you of areas impacted by where at least 10 trees per acre were killed. And now this map, And now this map that I'm showing is all areas where beetles were presumed to have killed trees, no matter how many trees per acre. And so I just show this map to show that nearly all forested regions in the Southwest have been influenced by beetles in the last 15 years or so. Here's a picture that I took at Bandelier National Monument. This is an area where in the 1940s there were ponderosa pine all over the place. This area was documented in Craig Allen and Dave Brashear's 1998 PNAS paper, where they document a huge amount of ponderosa pine mortality in this region, and effectively a conversion from ponderosa pine forest to pinyon juniper woodland. Besides the one lucky pine that you see here, it's mainly juniper trees that we're looking at. And so in the 1950s, they say, basically a type conversion of this region began. If we just walk a little bit away, now the area in the red box is the area that we were just in, and now we're looking at a pinyon juniper woodland, and in the foreground you see pinyon pine trees that are dead. It's very difficult in this area to find any live pinyon pine, and this is due to the bark beetle outbreak in the early 2000s that turned this pinyon juniper woodland into more of a juniper woodland. So continuation in this type conversion of the region. And the reason I was out there hiking around is because I was helping out my friend Henry Adams do sampling of juniper trees. The brown trees that you're seeing in this figure, which is taken, this picture, which is taken very near the last picture, are dead and dying juniper trees. And so we may now be seeing the beginning of a type conversion from a juniper-dominated woodland to something else. At the very least, we're seeing a conversion in the composition or the density of junipers in this area. Finally, we'll look at wildfire. This bottom panel is now showing the annual area where moderate or severe wildfire occurred within forest and woodland in the Southwest, according to Landsat and MODIS-derived satellite estimates of burned area. This goes from 1984 through 2012, and if we throw on the Forest Drought Stress Index, we again see a really good relationship here. Surprisingly good, I would say, given that humans, I think, add a lot of randomness into the system by starting fires and then making decisions about how to manage fires once they're put out. The strong relationship that we see here is consistent with the relationships that are derived from fire scar records from before the era of intense fire management. Again, the y-axis here on the burned area side of this figure is exponential, or logarithmic, indicating an exponential relationship between forest drought stress and area burned by wildfire. This map here is now showing area that has been burned by moderate or severe wildfires since 1984. The large ones stand out, but it really account for most of the area burns in the last 30 years are the Rodeo-Chudesky fire, 2002 in Arizona, the Wallow fire, 2011, the Las Conchas fire, 2011 in the Jemez Mountains in New Mexico, and the Whitewater Baldy fire that occurred this year in the Gila wilderness. Sorry, slideshow up in reverse again. So now we're looking at my backyard. These are the Jemez Mountains. The dot is showing Los Alamos, and we'll just look at fire activity in this region since the 1950s, which began in 1954 with the American Springs Fire. You see that little orange area showed up. Then in 1977, a larger fire. In 1996, the Dome Fire. In 1998, the Oso Complex Fire. 2000, the Cerro Grande Fire, which burnt into the town of Los Alamos. And then most recently in 2011, the Las Conchas Fire. And so people who've lived here for the last several decades have really watched their landscape transform in a major way. This is a picture that Craig Allen took shortly after the Las Conchas Fire. This is the site of the Dome Fire in 1996, which burnt fairly intensely. Then what grew back following that fire was mainly an oak scrub, and then in 2011, that landscape again burnt very severely. And what we're looking at now is a moonscape. We've talked to Craig. He's very doubtful about forests naturally regenerating in this area anytime in the coming decades. So what are the implications for the future? I make some inferences about the future by first looking at the past. Because these are tree ring records, we can look back a lot further than just 100 years. This is the regional tree ring record for the last 1,000 years, and some notable characteristics of this are very large droughts that are as large or bigger than the drought that we're in now. There's 1950s drought, which, let's see if I can use this highlighter then. There's 1950s drought here, which was documented to have caused some die-off of forests in the Southwest, such as in the Jemez Mountains. And the 1500s drought, which is here, was one of the largest mega droughts of the last millennium, and this drought is presumed to have killed a lot of trees in the Southwest. That conclusion is derived from tree ring demography studies. And there's the 1200s drought, which we know less about, but it also seems as though a lot of forest died off during this drought. Certainly that drought is famous for its influence on the ancient Puebloan society. And so we can kind of see that when we have droughts that reach a certain magnitude, then we can presume that there's going to be a lot of forest mortality in the Southwest. And we're just going to we're going to say, okay, in a year that is more intense than the most intense half of years during the 1500s mega drought might be a year that could contribute to regional forest mortality. And if we have a bunch of these years in a row, then we can assume that a lot of forest mortality will occur the same way that it seems to have occurred during the 1500s, the same way that it occurred on a smaller scale in the 1950s, and the same way that it is occurring now in the 2000s. And going back and using that really good relationship between climate and forest drought stress in the Southwest, we can now take projections of a cold season precipitation, which is shown in the top figure, and warm season vapor pressure deficit, which is shown in the bottom figure, and use these projections to project out future forest drought stress. The black time series that just appeared on these figures are the observed records, and so the important thing here is that in terms of precipitation, even though models tend to converge on the conclusion that precipitation will decline in the Southwest, the trend in precipitation decline projected is really small compared to the interannual variability that's already been established in the last century. And so it's going to take a while before we can recognize any trend in precipitation as being statistically significant, or before we can attribute any given dry year to being a climate change type dry year. Warm season vapor pressure deficit, on the other hand, is expected to increase so much that the positive trend will swamp out the interannual variability that's been established over the last 100 years. The highest value you see there is 2002, and we see by mid-century or average year should have a warm season vapor pressure deficit that is as high as it was in 2002. So you can only imagine what a 2002 type year would look like superimposed on this trend. If we take these projections and put them together into our forest drought stress index equation, then this is what we get. The black line, again, is the black time series is the observed record, the tree ring record, and then the red time series is our projection. And the black bar that you see going across, that horizontal black bar, is showing that threshold that I showed you a couple slides ago. It represents the average of the most severe 50% of years during the 1500s mega drought. And so we see that by the middle of this century, by the 2040s, to 2050s, our average year will have a forest drought stress index that was as severe or more severe than the worst years of the 1500s mega drought. Given that the 1500s mega drought looks like it killed off a lot of forests in the Southwest, and less severe droughts since then have killed off a forest in the Southwest, I interpret this to mean that change in the landscape of the Southwest is inevitable within the next 40 to 50 years. There will continue to, of course, be periods of drought and then wetter periods, but the droughts should continue to intensify due to increasingly high vapor pressure deficit, and the wetter periods should continue to be less wet, or should I say they should continue to correspond with a decreasing, with increasing forest drought stress as well. Importantly, effects on forests and effects on society as well don't occur during average years. They occur during really extreme years. Right now, we're looking at the 1,000-year tree ring derived record of extreme years. I call an extreme year a year that falls beyond that black bar in the last figure, a mega drought type year. And this time series I'm showing is a 50-year running mean, or a 50-year running frequency of those really intense drought type, mega drought type years. On average, about 4% of years in the last millennium have been these mega drought type intense years, with a peak of 18% in the 1200s. And if we project in the next century using model data, that we see that this running frequency of mega drought type intense years is supposed to go off the charts. According to the business as usual A2 emission scenario, by the end of this century, 80% of years are these intense type years. In the more optimistic emission scenarios, we see quite different results, but the same result in terms of the frequency of these intense years is projected to be like nothing that we have seen in time in the last 1,000 years. So speaking of intense years, most recently I've been looking at 2011. This year our time series, satellite-derived time series of burned area. In 2011 is really this really intense year, mainly because of the wildfire and the Las Conchas fire. But we see that forest fires were probably higher in 2011 than they were in the last 30 years and probably in the last 100 years. Non-forest, mainly grassland fires, were record-breaking in 2011. And then the total amount of forest area in the Southwest was record-breaking in 2011. So let's just look briefly at 2011. What were the climate things that were going on then? This here is a map of the 2011 vapor pressure deficits anomaly in standard deviation space relative to the last 118 years. And what we see is that in the eastern part of the Southwest, in West Texas especially, we see vapor pressure deficits approaching 6 standard deviations above the long-term mean. The time series on the bottom is now showing that long-term mean, and the text got kind of screwed up there, but the arrow is pointing to the 2011 value. And so I think that it's worthwhile to now just show the relationship between the area burned in the Southwest and April through June, spring and early summer vapor pressure deficit, there's a fairly strong relationship there. But in 2011 was a really interesting year because vapor pressure deficit, while it is usually driven by temperature, in 2011 it was actually more driven by dew point. 2011 had exceptionally low dew point in the Southwest. It was fairly warm, but the dew point was off the charts low. Made the Southwest look like it had been transplanted onto another planet temporarily. And so we're now seeing that in eastern New Mexico and West Texas we have dew points that are approximately 6 standard deviations below the long-term mean. And so I wanted to see, well, what caused this? And what I found was mainly that it was natural variability. The low dew point was primarily driven by a very strong pressure gradient between high pressure over the North Pacific and low pressure over the continent that drove very strong and persistent winds down the coast from the north. Air coming out of the north tends to be dry, and it was sweeping across the Southwest. Soils were dry in the Southwest. The strong winds helped to dry out the soils even more. The winds were dry themselves, and then now this green line here is showing the average trajectory of winds, of lower tropospheric winds in the Southwest. If we take the atmosphere and now look at it along its profile, along that green line, then this is what the wind anomalies looked like along that profile, where the bottom of this figure is showing the ground. See that green line moving over the mountains in the western U.S. The top of the figure is approaching outer space, and the arrows are moving parallel to that line, and we see that not only was it windy at the surface, but it was very windy along this trajectory throughout the entire atmospheric profile. And not only were winds moving horizontally anomalously quickly, but they're moving vertically down anomalously quickly. There's subsidence over the Southwest. Subsidence of air produces dry conditions. The upper atmosphere is dry. We have dry air sinking toward the surface, contributing to the dryness of the Southwest and contributing to this wind speeds at the surface. Now this map in the upper part, this figure, is showing wind anomalies immediately at the surface, as well as winds divergence. The colors are showing divergence of winds, and divergence is basically spreading of wind. We see that in the Southwest, in the western part of the Southwest over Arizona and New Mexico, wind was spreading exceptionally quickly. This is because air was sinking above. It's basically a traffic jam of air, and air is having to spread away at the surface. And you can see that it's all being funneled toward West Texas. Spreading of this accelerating dry air from the north as well as from the upper atmosphere is hitting the surface in the Southwest and being funneled toward Texas, and this contributed to the extremely dry conditions in Texas. Not only dry, but extremely warm and record-breaking vapor pressure deficits in eastern New Mexico and West Texas. The time series here is showing a time series of 7-day average divergence in the Southwest. The black line in gray area shows what is expected based on the last 34 years or so of climate data, and then the 2011. And then the 2011 conditions are shown in the red line. You can see that this divergence was pretty persistent throughout the entire season. So I'll conclude by just asking the question, how might warming impact forests in the future? Here's a map showing 1990s forest and woodland distributions, and now this map is showing just what has happened in the last 15 to 30 years. Again, orange areas are areas where bark beetles have eaten away trees. Red areas are areas that have been burnt by stand-replacing wildfires. And if we look to see what are the drought conditions like in these places, we see, let me go to this last component of the talk. Let me back up now. So the green area here is basically a histogram of forest drought stress values in the Southwest. These are mean annual values. You can see that these represent all the locations where forest or woodlands are present in the Southwest, where more negative means more drought, less negative means less drought. And then the brown area is showing a histogram, but for areas that were killed by bark beetles or wildfire. And we see that it is a bit skewed to the left, meaning that wildfire and bark beetles have been slightly biased toward areas that are not wet and cool. The coolest and wettest areas so far have been the areas where we have seen the least amount of forest fire and bark beetle activity. And what this says to me is that maybe there's some hope for the future. Certainly there are places in the Southwest that are so wet and so cool now that even with a 4 degrees Celsius warming, they should still have a climate that is suitable for some forest species. Those forest species may not be there now, but maybe this is the time to start thinking about what it would take to get those forest species there. If we as a society decide that we really like having forests in the Southwest. I believe my work shows that change in the southwestern landscape is inevitable because of climate change, but if we want to preserve forests in some places, I think it may take some work on our part. It may also take some work to preserve some forests that we believe can survive the next century of climate change by protecting them from very large wildfires, like the Los Conchas fire. Here's another picture that Craig Allen took in the Jemez, and this is showing an area that he estimates to be part of a 30,000 acre patch of death that was ponderosa pine forest. He anticipates that it would be centuries or longer before ponderosa pine could naturally regenerate in this area. And this is an area that was historically fairly wet and fairly cool, but it was subjected to a very large and intense wildfire, partly driven by very dense forest in the region. And so our forest density is obviously something to be thinking about, and when we think about wanting to shepherd some forested areas through the next century, I think it's going to be important to try and protect those forests from very large and intense wildfires that are driven not only by drought, but by high forest density. Importantly, this study is showing a pretty broad paintbrush type view of the Southwest, where we say droughtier places are more susceptible, and those droughtier places are defined using a fairly coarse resolution of climate. But I show this figure. This figure is taken from the Mogollon Rim looking down the valley near Payson, Arizona. And down in the valley you can see this large swath of pine forest. And this is an area where my study might say, oh, we can't have forests there in the next 100 years. But people who are experts in that area may say, well, this is a cold air drainage, and it's in a well-drained soil river valley, and forests here are not very drought stressed. And so my results here should be interpreted with a grain of salt by people who are experts in their local communities or local areas that they know very well. And they can hopefully take the broad and general rules that I've laid out and decide for themselves how effectively those broad and general rules can be applied to their region of interest. And finally, I'll just conclude by saying that I find that vapor pressure deficit throughout the southwestern region, on average, is at least as important as cold season precipitation in the region, and that drought stress in the region corresponds exponentially with vulnerability to large mortality mechanisms like bark beetle outbreak and wildfire. If climate models are correct, then by the 2050s, forest drought stress should exceed 1500 mega drought type levels, and that should correspond with large forest die-off. Importantly, die-offs should occur rapidly due to extreme years, not average years probably. Extreme years like 2011 superimposed on the vapor pressure deficits of the 2080s will be like nothing that has been seen in thousands and thousands of years in the Southwest, I'm sure. Importantly, some wet, cool regions may be hospitable for forests in 2100, but it may require some help for humans in order for them to survive. And that's all I have to say. Thank you.
Well, thank you so much, Park. That's a little bit depressing presentation, but good to have the facts, and you've laid it out very clearly for us. I'll go ahead and unmute the line momentarily, so if you have a question out there, you can begin formulating it. And if you're eating your lunch or listening to the radio in the background, please go ahead and mute your phone on your own personal end. As a moderator, I'll take advantage of my position and ask the first question. Park, as you look at some of the bark beetle impacts and now your most recent work on fires, to what extent are you able to take into account the geography, the spatial patterning, particularly given that many of these issues, both bark beetle and in some cases high severity fire, are density dependent. That is, denser areas have very different impacts than areas that are less dense. And I think the contrast between, say, the wallow fire and the whitewater baldy is a good example of that. But
yep.
Obviously, much of your work is kind of at a regional level, so maybe that's not something you can build in.
Yeah, well, that's a really good question. Thus far, I haven't done a whole lot of spatial work. I've done some, but again, making really broad assumptions. Using these fairly coarsely scaled data sets. 4-kilometer climate data, which smear out a lot of really important finer scale climate processes, as well as these pretty coarse maps that just tell us where there's forest or woodland, broadly defining forest as non-pinyon and juniper, and broadly defining woodland as pinyon and juniper, and not considering forest density at all, but it certainly is important. I got to visit the site of the whitewater baldy fire with Craig Allen, and I saw Pepe on this list. He's the one who organized the trip this summer. And it really was striking, the difference between the intensity of those fires. Whitewater baldy fire appearing to have to result in less actual severity in terms of tree mortality because that landscape is much patchier due to previous fires. And that's something that's not accounted for at all in this study, but it's certainly important. It's really important to recognize this forest drought stress index that we created is more of a climate index. But it's expressing climate's influence on forests from a forest perspective. But we're really, when we ask for the forest perspective, we're considering the forests of the last 100 years, really, because that's the period during which we calibrated our tree ring record versus our climate data model. And so in 2050, when we project a more severe forest drought stress index than any other time in the last millennium, we're really saying if the forests of the last century were there in the 2050s, then the average forest drought stress conditions would be more severe than they were during any time of the last millennium. Of course, very likely the forest distribution by 2050 will be different. And so very likely forests in many areas will be less dense, and so the trees that are surviving there may be more resilient to drought intensification than the trees that are in those sites today.
And that Barb just typed a question in the chat window that kind of gets to that same point and asks if you think that the Gila might be an example of a priority area for managers where we might be able to maintain forests for survival in the long term.
My impression is yes. I don't want to give the impression, though, that I am an expert by any means in forest management. But the folks that I was there with felt like the Gila Wilderness was proven to be somewhat of a success story in 2011 when we saw that, sure, the area burned was huge, but I think when the data come in to give us an impression of an idea for what the actual severity was, or the long-term influence on the species composition of the landscape, it won't be nearly as severe as the Las Conchas fire. And so my impression is that yes, the management decisions in the past few decades in the Gila Wilderness may be used as a model for other wilderness areas in the future.
And another question from Quentin Hayes about high-altitude mixed conifer forests, which might correspond in your study, Park, to the Douglas fir component, and thinking about whether these are microclimate areas that might be sustained, assuming density can be dealt with in one way or another.
Yeah, I think so. So you go up high, you get into spruce forest, and definitely there are these high altitude, high elevation forests in the Southwest that are probably much more resilient in the way that even with a 4-degree warming, maybe there will still be enough water availability and vapor pressure deficits will still be low enough that the trees that are there are okay. On the other hand, it has been shown recently in Nature paper by Choate et al. That many forests globally, even forests not traditionally known to be drought sensitive, are equally vulnerable to drought by cavitation. Basically, they can only suck on the soil so hard before they have to either die or close their stomata. And in this way, every individual tree at these high altitude places may be specifically tuned to a certain amount of soil moisture or a certain degree of vapor pressure deficit. And so a stepwise type transition in vapor pressure deficit, even in these coolest, wettest places, may cause damage that doesn't make a whole lot of logical sense to us, just assuming that drought stress should be highest at the warmest, driest places. There's some new work that may be coming out somewhat soon looking at seedlings in the central U.S., and this work indicates that trees that develop in cooler conditions actually may be more vulnerable to increases in vapor pressure deficit because they do not undergo some adaptive processes that will lead them to have more sensitive closure of their stomata or ability to close their stomata in high VPD situations, as opposed to trees that do establish in higher VPD situations that somehow adapt the ability to be more sensitive and close up shop during periods of intense VPD or drought.
Okay, I'm going to go ahead and unmute the line, and in the hopes that Andy, maybe you can ask your question right over the line. Andy,
Hello.
are you there?
I am. Can you hear me?
Yes.
Yes.
So I just had a question related to basically the average FDSI around 2050 being comparable to the worst 50% of the historic. That doesn't really include that sort of a time frame prediction there. It doesn't include any feedback from fire, does it?
No.
So because the question is, your FDSI seems to track very well also with wildfire area, I believe it was.
Yep.
And so you would also expect larger fires to continue as that FDSI increases at the same time, so that the time frame that you're talking about could actually be shorter.
Yeah, well, that's an interesting point. So this FDSI, again, is kind of this weird climate variable, where really what I'm saying is that the climate conditions the drought conditions that corresponded with forest drought stress in the last 100 years should become so severe in 2050 that those climate conditions are worse than any other time in the last millennium for forest health. But absolutely, what we see by comparing the forest drought stress index to burned areas is this exponential relationship, not only on a decadal type time scale, but interannual, meaning that the observed increase in burned area is not only due to a increase in forest density or changes in or trends in forest fire management decisions, but it really is driven by drought intensity as well. And so certainly before 2050, I would expect that the landscape should be looking very different than it's looked any time in our since our modern society showed up here in the Southwest.
Yeah, and it's even a little more disturbing that we've got some data from the last 28 years of burn severity, and we're finding a really strong relationship between overall fire size and the largest high severity patch. So basically, as that FDSI, if you see that increase correlating with wildfire size, we could also consider that that correlates strongly with the largest high severity patch size, which is even worse for the site conversion concept is accelerating.
Right. Right. Yeah. That makes sense, and so that's why I at least mentioned the idea at the end of my talk about the idea of potentially assisting species in repopulating some of these large patches. Obviously, that may end up being a very contentious issue. That all the feedback, something like that, would need to be looked into, I guess.
So we're closing in on just about an hour, and so obviously if you want to drop off the line, that's fine. Please do fill out the survey that should appear when you close off the webinar. But if you want to stay on the line and ask a few more questions, that's fine too. Brad Hawks, are you still on the line?
I am indeed.
So you had a question about cultures, and maybe I'll just let you go ahead and ask it.
Yeah, I just wondered if there's some archaeological evidence of what happened to people and cultures back in the 1500 mega drought.
Yeah, so I think that what I've been told is that the archaeological evidence for this, for impact on societies during that drought, is a little more ambiguous than it was during the 1200s. In this region, northern New Mexico, I do know that the Native American populations pretty rapidly moved from mesas down to river valleys during the 1500s drought, and that the presumed reason for that is to be able to take advantage of the more reliable source of water in the river. Craig Allen is the one who told me that, and beyond that, I don't know. I spoke with a co-author of mine, Jeff Dean, who is one of the leading longtime archaeological researchers in the Southwest, and he says that he's had a difficult time finding any evidence of definite cultural response to that 1500s drought. So that kind of contradicts what Craig told me more recently.
Thanks.
Hello?
Hey, I had a question. Hey, Park, can you hear me?
Yes.
So my question is, so is there a website or a way that people can calculate the vapor pressure deficit, like the current one and maybe the predicted for the fire season?
Yeah, there are. So the vapor pressure deficit is a fairly standard calculation. You can find it if you just do a Google search for vapor pressure deficit, then you should be able to calculate it yourself. I outline it in my in the supplementary online section of my Nature Climate Change paper.
Okay.
But it's basically, so the vapor pressure deficit is defined as the difference between how much water vapor the atmosphere can hold and how much water vapor the atmosphere is actually holding. And so there's an equation that relates temperature to the saturation vapor pressure, or basically the amount of water vapor the atmosphere can hold at any given temperature. And so if you just apply that equation to the actual temperature and then again to the dew point temperature and take the difference, then you get your vapor pressure deficit.
So and is that something like the climate people kind of predict and kind of map out for the upcoming fire season? Do you know?
Yeah, I think it can be done. I can certainly do that.
All right. I was just wondering.
Yep.
That might be worth something to talk to the climate people, to kind of put in their because they I think publish those monthly reports. I think that would be interesting to see.
Right. Well, that's definitely what I'm pushing for, Pepe. I think that it's really important. This vapor pressure deficit variable, even though I think like it's a fairly standard variable, it amazes me how it is not recognized. Its importance isn't recognized, at least as much as I think it should be. People still, mainly people talk about temperature, but and temperature's influence on forests and on fire vulnerability. But I think they're using the term temperature out of convenience, and certainly the more accurate term is the vapor pressure deficit.
Okay, thanks.
Other questions or comments? Okay, well, I think I'd like to thank you again, Park, and again, it's a bit daunting thinking about the management challenges as an implication of your research, but certainly important to go forward with our eyes open to the coming changes. So I really appreciate your time, and I thank everybody for participating today. I hope everybody enjoyed the webinar. And again, fill out the survey when you have the chance, and the webinar recording will be available soon. So thanks again, everybody.
All right. Thank you, guys.
Thanks, Xander.
Thanks.
Thank you.